Welcome you all for the NPTEL online course on Smart Grid, and today we will be talking about the analysis aspect of Smart Grid. Now, as you have seen almost during last 13 to 14 lectures, where we focused how to develop a smart grid, different components of smart grid and their hardware implementation and analysis. But if you take into a system level, means you have a distribution system having few nodes, few hundred of nodes, and at one node the microgrid may exist, means the microgrid not necessarily to be established at each and every node of the distribution system, but certainly few zones of the distribution system. Now, the question is, when we determine the line currents as well as real power flow, reactive power flow, the voltage at each and every bus, then ideally we have to carry out a load flow analysis, and based on which the potential at each and every node can be determined, that will indirectly tell me the health or the system state. But when you establish smart grid or microgrid at different locations of a distribution system, then the system analysis, especially when you determine the voltage at each and every node, and the algorithm need to be made more robust, and which is slightly complicated compared to the classical load flow analysis. Now, the very standard load flow analysis which has been used in distribution system, let us say it is a forward backward sweep algorithm, where we have the substation or the bus, initial bus, and then we have a load bus, and in between there could be couple of buses. Now, considering the system is purely radial, and when we see that the load is of x kVA and the source is expected to operate at 1 per unit for an example, and now what happens, the voltage which is keep on dropping because it is radial, and finally the voltage is altogether different compared to my substation voltage. So, if you start with 1 per unit in a radial system, the last bus may experience a voltage which is close to 0.85 or 0.88. Now, the concern here, how do you determine voltage, because the system is altogether different, and the conventional Gauss-Seidel Newton-Raphson algorithms cannot be extended to distribution system, being the system is of high R by X ratio, and those algorithms cannot be extended, means the transmission system load flow algorithms cannot be so easily extended to distribution level of low voltages, and hence we have to go for a new algorithm, that is forward backward sweep as an example, where we consider that the voltage at the last node is same as my substation voltage. So, knowing the power requirement at that bus, assuming the voltage as 1 per unit, we can determine the current, and further we can determine the voltage by adding the drop, and further we can determine the voltage adding the drop, and so and so. And when you reach back to your from the load point to the substation, we will come to know the voltage is keep on adding 1, 1.1, 1.15, so and so, and finally the substation voltage may be at 1.25 or 1.3, because we had an assumption that the last bus will experience 1 per unit voltage. But because my real voltage is expected to be 1, and because there is a mismatch from 1 to 1.25, the current is not acceptable to me. So, what we do? We assume the voltage once again as 1 per unit at the substation. Based on the previous current, we move further. The voltage is known 1 per unit, the current which has been determined based on the previous step, and then you determine the voltage, and you experience, let us say 0.98. And you keep on oscillating from the last node to the substation node, and from the substation node to the last node, and hence it is called forward backward sweep. And you keep on doing it, repeat the exercise till the substation voltage is very close to 1 per unit, or the difference between the voltage which has been determined after sweep must be very close to my substation voltage, and then I can claim, oh, that is what the situation is. All the voltages with respect to the last iteration, assuming the substation voltage is 1 per unit, will be my voltage solution of the network. And these are, but now when you have a smart grid in place, then so many new devices, new converters, those have not been modeled in my conventional load flow algorithm. So, the cable modeling, the line modeling, the transformer modeling, the load modeling, the source modeling are common, but the distributed generator modeling, PV modeling, storage modeling and the converter modeling become the new components that a distribution system can experience in the presence of smart grid. So, now the challenge is, how do you simulate or analyze a system, a distribution system having smart grid along with renewable generations, cables, converters, batteries, etc. And that grid could be a DC smart grid or AC smart grid, or could be a combination of AC DC smart grid. So, let us now move on to the system analysis of distribution system in the presence of smart grid. Now, first of all, we will just cover this portion with different steps like AC-DC distribution network, structure of AC-DC distribution network, classification of buses, overview of load flow analysis, AC-DC load flow analysis and their challenges, power converter modeling, distributed generator modeling and basic steps for formulating AC-DC load flow. Because when you talk about a DC microgrid along with a AC distribution system, so my system become AC distribution system and a DC microgrid in place. So, then the scenario could be AC-DC distribution system, and we have to now have a load flow algorithm which is suitable for AC-DC system simultaneously. So, what is AC-DC distribution network? Now, in the late 1880s, three exceptionally brilliant inventors, Nikola Tesla, George Westinghouse and Thomas Edison, battled over which electricity system, whether it has to be alternating AC in nature or DC in nature, and which one has to be the standard for future. But due to numerous advantage of AC over DC, finally AC found to be the victorious one, and today we all use AC system in place. Owing to the ever increasing demand, declining conventional energy sources and technology revolution in deploying renewable energy sources, interest is invoked towards DC grid again. Though we have mentioned that the AC system is considered to be the victorious or the meritorious one, but looking into the current scenario of maximum renewable penetration into the system, slowly the DC network or the DC grid taking upper hand over AC. But being said that, we cannot absolutely replace the AC system. It is both, they have to exist together and simultaneously. There are various advantages of DC over AC, but the complete reinforcement of the existing distribution system is next to impossible, and hence DC seems to be impracticable at this stage. So, what we have to consider that the AC system is in place along with DC, a part of the distribution system could be of DC in nature, but the replacement of AC system by DC is next to impossible. So, researchers are planning a hybrid distribution network with both AC and DC grids. Now, if you look at the structure of a AC-DC system, it may look like this. So, previously let us say the system is completely AC, where we have the source and further we have different buses, and let us see all, it is radial in system, it goes this way as well as this way, and you can see few rings in between loops. and all the buses are AC in nature, which was the initial stage. But now we are considering that there could be few DC microgrids in place. So, most of the buses are not necessarily AC, but they could be DC. So, all the orange color marked in this diagram belongs to my AC bus, and all the blue color represent my DC bus. So, we can see that these are all AC buses, and this is the AC network, and we have DC buses and DC network and DC network. Now, please try to understand, when you talk about the loads, those loads are not necessarily to be purely AC or purely DC, and hence loads can be connected, means AC DC loads can be connected at a DC bus as well as at a AC bus. And because of that, conversion from DC to DC, DC to AC, AC to AC and AC to DC is very, very common. Now, what are the major components of a AC-DC network? And the AC-DC distribution system consists of variety of AC-DC components, including loads, generation units, lines and buses. In addition to traditional AC loads and AC generators, it can also include DC loads and DC generators, and perhaps we can include electric vehicles, PV panels, etc. Renewable technologies like PV systems, wind generators also can be considered in our system modeling. Now, power converters, which considered to be one of the very, very important part here, because in our previous distribution load flow analysis, we ideally do not consider the modeling of power converters. But when you talk about smart grid, certainly it has many converters, and without modeling power converters, your AC-DC load flow has no meaning, all right. So, how do you classify? Because as you know, in any system, we ideally have actually three different types of buses. One is known as slack bus, and whereas you consider that the voltage and angle at that bus is known to you, and whereas the P and Q requirement at that bus is not known to you. So, out of all four parameters P, Q, V, delta, that is real power, reactive power, voltage at that bus and angle. Now, two parameters, those are V and delta, are known to me, whereas P and Q, which are not known to me, is known as a slack bus. Now, moving towards a PQ bus, where the P and Q are known to me like a load, whereas V and delta is not known to me. And in case of a PV bus, where the P is known to me, real power output is known to me, the voltage at that bus is known to me, but the Q and delta is not known to me. So, the main challenge for a load flow analysis is how to determine the rest of the two parameters at each and every bus which is not known to me. So, at the end of the day, we can determine all the four variables like P, Q, V, delta at each and every bus of the system. So, I can say the system analysis of a AC system is clearer. But when you go for your DC buses, now the reactive power is missing, the angle is missing. So, perhaps you have only P and V, the real power and voltage, because a DC system. Now, in DC bus, we have a P bus where we call it as a DC load bus or so called P bus, where the net DC power injected into the bus is known while the voltage is not known. The P is known, but the V is not known, so called DC load bus or P bus. Now, we will have one more bus called as VDC bus, that is DC voltage controlled bus, where the DC bus voltage is known, but the power generated at that bus is not known. First one is P is known, V is not known. The second one where V is known and P is not known. So, you can clearly see, now this is my AC bus where we can connect AC distributed generators, we can connect AC loads, we can perhaps connect DC loads, and you can also connect DC distributed generators. Similarly, when you model a DC bus, I mean we can have DC distributed generators, we can have DC load, we can have AC distributed generators, and you can have AC loads. Now, very quickly the overview of load flow analysis. For proper planning, analysis and optimal operation of transmission or distribution system, a power flow or load flow analysis become a must. Now, load flow study is a steady state analysis whose target is to determine the voltages, currents and real and reactive power flow in the system under a given loading condition. So, if the loads are known to me, I must be in a position to determine the voltage at each and every bus, the real power, reactive power flow in each and every line need to be determined. Now, the purpose of load flow studies is to plan ahead and account of various hypothetical situations. If the load scenarios are keep on changing, how do I plan my system so that the voltage at each and every node do not violate the permissible variation, maybe 2%, 5% depending upon the utility. Now, there are well established algorithms for Newton's Newton-Raphson load flow, Gauss-Seidel load flow algorithms, fast decouple and Broyden methods. But unfortunately, the distribution system do have high value of R by X ratio and they are weak in nature and mostly they are radial. And because of that, those transmission system based algorithms cannot be simply extended as it is to my distribution system. They need to be updated and modified to suit to my current environment where the R by X ratio could be high, the system could be radial and it is weak in nature. Now, the very important AC-DC distribution system is more complex compared to a AC distribution system. It has many elements like new generators, converters whose input and output relations are extremely nonlinear, and hence the modeling or developing algorithm for AC-DC system become a challenge. Now, when you move to AC-DC load flow analysis, what are the challenges? Proper modeling of various types of power converters in the load flow equations become important. So, how do you incorporate those modeling into your system so to make it more generic? And modeling of various types of distributed generators like PV systems, wind generators, etc. And modeling of storage and various DC loads. I mean the storage need to be modeled and the DC loads also need to be modeled. And finally, taking care of prerequisite control objective by the converters in the load flow equations. The control characteristic of those converters need to be embedded into my load flow. The load flow equations must be capable of modeling the operating state of the combined AC-DC system under the specified conditions of the load generation AC-DC system control strategies. Now, there are two different important models that need to be developed. The first one is AC-DC VSC converter model, where you can clearly see that is my point of common coupling. We have VPPC and the PCC, then we have the impedance and then the final output voltage in AC, and then you convert to DC from AC to DC through a VSC, and finally you experience the terminal voltage which is VDC, and there could be a drop in my DC grid, and finally you experience VDC. So, what exactly happened that from the point of common coupling, the voltage is V and then different stages it get dropped down, and then because of the line impedances, and finally you convert to DC, and there could be a couple of drops in the DC lines or DC cables, and the terminal voltage could be VDC at kth bus. Now, one more important model, that is DC-DC converter model, where there are few equations where you could see that the DC-DC converter and the bus at 1, and you can experience the bus 2 with a new voltage through a DC-DC converter, and the following mathematical equations are used to model buck boost and buck boost, where equation number 9 and 12 is being used for buck type, 10 and 13 used for the boost type, and 11 and 14 used for your buck boost converters. Now, there is one more important converter known as AC-DC line commutated converter, that is LCC model. The PWM and DC-DC converters can achieve better control objective than LCC at the distribution level. Hence, these converters can be used between the buses as well as between DG and bus for transferring power by fulfilling the control objectives. But if you go for LCC, because they are not so precise, and in that scenario where measure control objectives are not highly expected, if you are not looking for measure control objectives, then LCC can be used between buses as bus to bus interfacing, but not as a DG bus interfacing. So, if you are connecting between bus to bus, please you can place LCC, but if it is between DG to bus, then it has to be it should not be LCC. That is what actually being recommended. Now, the pictorial diagram, a schematic diagram of LCC converter, where you are converting from AC bus to a DC bus and from bus number 1 to bus number 2, and this is how the LCC being represented or modeled in our analysis. Now, when you model, the next level is distributed generator modeling. We model distributed generators based on 4 types. There are type 1, type 2, type 3, type 4 modeling. And type 1 where this type of distributed generator is capable of delivering only active power such as photovoltaic fuel cells, which are integrated to the main grid with the help of converters and inverters. So, this kind of modeling we say only real power injection, which is of type 1. Then we will have type 2 where the DG capable of delivering both active as well as reactive power. So, it is not simply P, but it is P as well as Q, and we call it is type 2. And further we can move to type 3, DG capable of delivering only reactive power, that is such as synchronous compensators, such as gas turbine are the example of this type of where they operate at 0 power factor. So, you only consider the reactive power injection. And type 4 where you give the real power and take the reactive power out. So, DG capable of delivering active power, but consuming reactive power, as an example induction generators for the wind farms, etc. So, to conclude, all these type of distributed generators can be modeled in any one of these categories as PVDG or VDC-DG or PQ-DG or P-type DG while simulating the load flow equation. So, what in excess we are projecting here compared to the existing literature is that the DG based on type 1, type 2, type 3, type 4 can be modeled, different converters can be modeled, and they can take care of my new components within the DC smart grid, and hence I can simulate both AC distribution system along with DC smart grid simultaneously. Now, what are the basic steps for load flow formulation of AC-DC distribution network? First one, the mathematical model of both AC and DC distribution lines and cables is required. There should be proper mathematical modeling of various types of loads associated with AC and DC distribution system. The most important part is modeling of various types of converters, taking care of control objective that need to be achieved. Modeling of renewable generators like your PV, wind, could be of PV type, VDC type, PQ type or P type modeling is also required to represent your type 1, type 2, type 3, type 4 DGs. And the suitable unified sequential approach is required to simulate all the mathematical model. And with this I like to conclude that the distribution system analysis in the presence of DC microgrid become an important issue, and we need to appropriately model those new components, especially the distributed generators of type 1, type 2, type 3, type 4 along with different converters, so that the voltage profile system planning for a AC-DC distribution system along with smart grid presence can be viable. Thank you.